4.5 Metallic bond. There are 4 learning outcomes that I'm going to cover in this video. The first one, I'm going to explain the formations of metallic bond using electron C model. And then I'm going to relate metallic bond to the properties of matter such as malleability, ductility, electrical conductivity, thermal conductivity. And third learning outcome, I'm going to explain the factors that affect the strength of metallic bond. And the last one, I'm going to relate melting and the boiling point to the molecular structure, types of bonding and intermolecular forces for element in period 3, group 1 and group 17. In a metal atoms can be imagined to be as an array of positive ions immersed in a sea of delocalized valence electrons. And these delocalized valence electrons are not bound individually to atoms, but they are mobile and bind loosely to large number of metal atoms. And what is metallic bond? Metallic bond basically refer to electrostatic forces between the positively charged metal ions and the sea of delocalized valence electrons. And metallic bond of a metal can be described using electron C model. This is the diagram of electron C model, and based on this electron C model, we can see that in a metal, it consists of positive charge metal ion in a fixed lattice point and surrounded by the sea of delocalized valence electrons. And basically, what is metallic bond? Metallic bond refer to the electrostatic forces between the negatively charged sea of delocalized valence electron with the positively charged metal ion that give rise to the metallic bond. Metals, because adopting this metallic structure causes them to lose their valence electrons easily, because the valence electron forming the sea of delocalized electrons, and it is not bound to any of the individual atoms, but is loosely mobile in a sea of delocalized electron as in the electron C model. We are going to use the electron C model to describe the metallic bond in magnesium metal. Based on the electron C model, basically in magnesium metal, the magnesium metal ions are in a fixed lattice point. So at each fixed lattice point, it consists of magnesium metal ion. At each of the fixed lattice point, it consists of magnesium metal ion. And each magnesium atom will provide 2 valence electrons to form the sea of delocalized electrons. Each magnesium atom contribute 2 electrons to form the sea of delocalized electrons. And what is metallic bond? Metallic bonds is referring to the strong electrostatic forces between the sea of delocalized electron, which is negatively charged, with the positively charged magnesium metal ion. Now we move on to look at the properties of matter. Basically, the physical properties of matter are result from the delocalizations of the valence electrons involved in metallic bond formations. So the first property of matter that we are going to look at is ductility. Ductility basically refers to the ability of a metal to be pulled into wire. When an external force is applied to pull the metal ion, they can slide past each other to the new lattice positions without repelling each other. Because of this, the metal is ductile and can be pulled into wire, such as the copper wire that we use in the electric cable. The second property of matter is malleability. Malleability basically refers to the ability of a metal to be flattened into a sheet. When a piece of metal is being hammered, the metal ions again can slide past each other to the new lattice positions without repelling each other due to the presence of the sea of delocalized electrons. Due to this, the metal therefore can be hammered into a thin sheet and this property of matter we call it as malleability. The third property of matter is related to its ability to conduct electricity. Due to the presence of the sea of delocalized electrons, matter is able to conduct electricity. The fourth property of matter is related to its ability to conduct heat. Again, due to the presence of the sea of delocalized electrons in matter, matter therefore is a good heat conductor and usually is the chosen material to make cooking pot. Now we move on to look at factors affecting the strength of metallic bonds. Basically, there are two factors affecting the strength of metallic bond. The first factor is the size of metal atom. Smaller is the size of the metal atom. Stronger is the electrostatic forces between the metal ion and the sea of delocalized electrons, and therefore stronger will be the metallic bond. In other words, we can say that the strength of metallic bond is inversely proportional to the size of the metal atom. Smaller the size, stronger is the metallic bond. The second factor is number of valence electrons. More number of valence electrons can be contributed by the metal atom to form the sea of delocalized electrons. More electrostatic forces therefore can be formed between the metal ions and the sea of delocalized electrons, and therefore stronger will be the metallic bond. In other words, we can say that the strength of metallic bond is directly proportional to the number of valence electrons. Larger number of valence electrons can be contributed by the metal atom to form the sea of delocalized electrons. Stronger will be the metallic bond. Now we move on to look at how the melting point and the boiling points change as going down group 1. Again, all the elements of group 1, they are metal, and therefore they have metallic structure, and within them there are metallic bonds. Again, the strength of metallic bond depends on the size of the metal atom. When going down the group, the size of the metal atoms getting larger. We know that strength of metallic bond is inversely proportional to the size of metal atom. When going down group 1, the size of metal atom increases. Therefore, we will expect the strength of metallic bond to decrease as going down group 1, as the electrostatic attractions between the metal ions and the sea of delocalized electrons becomes weaker as going down group 1. As the strength of metallic bond decreases as going down group 1, we will expect less energy is needed to break the metallic bond, and therefore as going down group 1, the melting point and the boiling points of the elements decreases. How about group 17 elements? Group 17 elements, they are non-matter and therefore adopting simple molecular structure. And the intermolecular forces acting between molecules are van der Waals forces. And the strength of van der Waals forces depends very much on the molecular size. As going down group 17, the size of atoms become larger. Therefore, we will expect the molecular size increases as going down group 17. We can see this based on the molar mass of the molecules. When going down group 17, as the molecular size increases, this will cause the strength of van der Waals forces to increase. And as the strength of van der Waals forces increases, more energy needed to overcome the van der Waals forces between the molecules. Therefore, as going down group 17, we will expect the melting point and the boiling point of elements to increase. Now we move on to look at the melting point and the boiling point across period 3 elements. For period 3 elements, we need to divide them into 3 classes, and different classes basically having different structure and therefore different type of bonds or intermolecular forces are going to affect the melting point and the boiling points of the elements. Now we move on to look at the first class of period 3 elements, sodium, magnesium, and aluminum. Sodium, magnesium, and aluminum, they are metal, therefore adopting metallic structure and have metallic bond. Therefore, the melting point and the boiling point across period 3 elements from sodium, magnesium to aluminum is very much depends on the strength of metallic bond. Again, the strength of metallic bond depends on two factors. The first one is the number of valence electrons that can be contributed by the metal atom to form the sea of delocalized electrons, and the second one is the size of metal atom. Across period 3 from sodium, magnesium to aluminum, the strength of metallic bond increases because the number of valence electrons that can be contributed by metal atom to the sea of delocalized electrons increases from sodium, magnesium to aluminum. Sodium can contribute 1, magnesium can contribute 2, while aluminum can contribute 3 to form the sea of delocalized electrons. As the number of valence electrons that can form the sea of delocalized electrons increases from sodium, magnesium to aluminum, therefore the strength of metallic bond increase from sodium, magnesium to aluminum. Besides this, from sodium, magnesium to aluminum, the atomic size also decreases. As the atomic size decreases from sodium, magnesium to aluminum, again the strength of metallic bond will increase from sodium, magnesium to aluminum. As the metallic bond becomes stronger from sodium, magnesium to aluminum, we will expect more heat energy needed to break the stronger metallic bond from sodium, magnesium to aluminum, and therefore the melting point and the boiling point is expected to increase from sodium, magnesium to aluminum. Now we look at the second class, the silicon, which adopt the giant molecular structure. In silicon, each of the silicon atoms is covalently bonded to another 4 silicon atoms tetrahedrally, infinitely in the silicon giant molecular structure. So the structure is shown in the diagram. We can see that each silicon atom is tetrahedrally bonded to another 4 silicon atoms, and this tetrahedral shape continue infinitely in the silicon giant molecular structure. As the covalent bond is very strong, therefore a lot of energy is needed to break the strong covalent bond in silicon, and therefore is expected that silicon has the highest melting and boiling point among period 3 elements. The last group is from phosphorus to argon. From phosphorus to argon, they are non-metal and therefore adopting simple molecular structure, with phosphorus exists as P4, and sulfur exists as S8, and chlorine exists as Cl2, and argon exists as monoatomic structure. As they are adopting simple molecular structure, therefore the attractive forces between the molecules will be the van der Waals forces, and the strength of van der Waals forces depends on the molecular size, and the molecular size increases from argon, Cl2, P4 to S8. Therefore, we will expect the strength of van der Waals forces to increase in the order of argon, Cl2, P4 to S8, and therefore the melting and the boiling point will increase from argon, chlorine, phosphorus to sulfur.